To completely describe the magnetic field at any point on the surface of the Earth, we have to specify its three elements at that point, namely declination, d, angle of dip or inclination, I, and horizontal component of the Earth's magnetic field, He. Let us study about these three elements in detail one by one. First, the declination. We all know that the Earth is spherical in shape. On this spherical surface, we can draw an infinite number of imaginary circles passing through the Earth's geographical north and south poles. All these circles have one common diameter, which is the line joining the geographical north and south poles, or the Earth's axis of rotation. These imaginary circles are called longitudes. Each of these circles, along with the Earth's axis of rotation, can be drawn in one plane. This plane is called the geographic meridian. The geographical meridian, when viewed from top, appears to be a straight line. Similarly, we can obtain the magnetic meridian by drawing a line from the magnetic north and south poles. This magnetic meridian also looks like a straight line when viewed from the top of the chosen point. At any given point, the geographical meridian and the magnetic meridian together look like two intersecting straight lines. The acute angle between these two straight lines is known as declination. It is denoted by the capital letter D. Declination changes from place to place on Earth. Declination is minimal at the equator and goes on increasing with latitude. The second element of the Earth's magnetic field is the angle of dip or inclination. A magnetic compass needle is provided with a pivot such that it can rotate freely about a vertical axis. The needle comes to rest when aligned with the magnetic meridian to indicate the magnetic north. If the needle were also provided with a pivot such that it can rotate freely about a horizontal axis, it would also rotate in the magnetic meridian plane. If the compass is placed in the northern hemisphere, its north end dips down from the horizontal position. If the compass is placed in the southern hemisphere, its south end dips down from the horizontal. The angle through which it dips with respect to the horizontal plane at that point is known as the angle of dip or the inclination, denoted by the capital letter I. In other words, inclination is the angle that the total magnetic field of the Earth, BE, makes with the horizontal surface of the Earth at a given point. The inclination is 0 at the equator and increases as the latitude increases. If this compass is placed atop the magnetic pole, it will come to rest in the vertical position. We can measure the inclination at any given point using a magnetic needle with a horizontal axis and a spirit level. The study of these elements help us to find the total magnetic field of the Earth, BE. To find BE at any point on the Earth, we take the help of the third element, the horizontal component of the Earth's magnetic field, HE, at that point. BE and HE are vectors. Let us now construct the vector diagram using all the three elements. Locate point P on the globe at which you want to determine the Earth's total magnetic field, BE. Draw a circle passing through the point P and the geographic north and south poles. This is the geographic meridian circle. Draw another circle passing through the point P and the magnetic north and south poles. This is the magnetic meridian circle. Draw a plane which is tangential to the sphere at point P. Draw a tangent PA to the geographic meridian circle at point P. PA lies on the tangent plane and represents the geographic north-south direction. Draw a tangent PB to the magnetic meridian circle at point P. PB also lies on the tangent plane, but represents the magnetic north-south direction. Construct a parallelepiped passing through P, A and B. Rotate the line PA in the tangent plane such that it touches the parallelepiped at B. This angle of rotation is the angle of declination D at the point P. The length of the line PB, to some scale, represents the magnitude of the horizontal component, HE, of the Earth's magnetic field at the point P. Rotate the line PB in the vertical plane such that it touches the parallelepiped at C. This angle of rotation is the angle of dip, I, at the point P. The line PC represents the magnitude and direction of the total magnetic field, BE, at the point P. Drawing this three-dimensional diagram is a cumbersome process. Instead, we can draw a two-dimensional view of the essential elements to determine the Earth's total magnetic field. Take only the plane represented by PBCD in the three-dimensional view and draw a two-dimensional view of triangle PBC. Draw a horizontal line PB with the arrowhead at B. The length of this line, to some scale, represents the magnitude of HE. Draw a line PC making an angle I with PB. Draw a line BC is perpendicular to the line PB with an arrowhead at C. Line BC represents the vertical component VE of the Earth's magnetic field. On the line PC, put an arrowhead at C. Line PC represents the total magnetic field BE of the Earth at the point P. We can now write the trigonometric relationships for the sides and the angle in the right-angled triangle. Sin I is equal to BC divided by PC, which is equal to VE divided by BE, or VE is equal to BE sin I. Cos I is equal to PB divided by PC is equal to HE divided by BE, or HE is equal to BE cos I. Tan I is equal to BC divided by PB is equal to VE divided by HE, or VE is equal to HE tan I.